Hello, good morning all. Hope everybody's safe and sound. My name is Carlos Girão and I'm here today to present on PTFE gaskets and how they're not all the same. I thank ChemTECH for making this conference possible during these difficult COVID times, and I hope everybody enjoys the presentation. Let's have a quick look in our agenda. We will start with a brief introduction showing the parameters that we use for this study, followed by the description of the experimental test methodology and the test rig used for the evaluations. We'll then bring a comparison of skived versus expanded PTFE and how the type of PTFE resin can influence the performance of the materials. We also show a comparison of different expanded PTFE materials available on the market. Finally, a conclusion about the results we found. This study is a summary of an ASME PVP paper we published in 2018. The details of the paper can be seen here in the bottom in case anybody wants to go and get more details. There are multiple ways of producing PTFE gaskets. In a very short and simplified manner, you have your inputs, resin, process, additives. That will lead to a product, and this product performance is directly influenced by your inputs. And there are multiple properties that can be evaluated, such as sellability, mechanical resistance, creep, etc. For this study, we chose creep for being such a critical property for PTFE. Creep, sometimes called cold flow, is the tendency of a solid material to deform under the influence of mechanical stress. Creep leads to decrease of gasket installation stress and consequently an increase in the risks of leakage. But how can we measure creep? EN 13555 is a standard that describes multiple test procedures for evaluation of gasket parameters, including creep. It has a test procedure to measure PQR, which is the creep relaxation factor, and it's measured as a residual surface pressure over the initial surface pressure. Therefore, you can consider PQR as the remaining percentage of the stress you have applied to your gasket. As an example, a PQR of 0.3 means that only 30% of the total stress you applied on your gasket at the installation time remained after the test. The test procedure is quite simple. You apply the selected load at a specific rate, then you hold it for 5 minutes and increase the temperature at a specific rate to a required test value. You then hold the temperature for 4 hours and record the remaining load. The PQR is calculated as described earlier. All experiments were carried on an Untitled testing machine, which you can see in the picture below. This equipment is a smart press with a hydraulic piston on the top. You can program multiple test procedures and it executes accordingly. It's composed of a load cell to indicate the forces being applied on the gasket, cooling plates, followed by thermal insulation plates to isolate the heating area. The heating platings right here are for high temperature testing. It has 3 displacement transducers and the flanges and gasket being tested. Now that we have talked about the tests we're going to perform, let's talk about the materials that we're going to test. Starting with the skived PTFE, hard PTFE, or sometimes called virgin PTFE. You add the PTFE resin in a mold and press it to form a billet. The material is done through a molding process. Since you're not laminating or stretching in any direction, you do not get any molecular alignment through this manufacturing method. Once you have your molded billet, it goes into a sintering oven and that's it. The sintered material is then machined or skived to the desired sheet thickness. The expanded process is a lot more complex. It starts with an extrusion. At this first stage, the process already adds chain alignments to the PTFE. The extruded is then dried before it goes to a stretching machine where further alignments are conferred. On the stretcher, the material is expanded in 2 directions, and that's why ePTFE is many times called multi-axially expanded PTFE. A succession of layers of this stretch film are applied and sintered to form a sheet and will confer specific properties to this material that we will see in the test results to come. Besides the difference in process itself we already saw, the type of resin used on the processes are also different. Skived PTFE commonly uses granular PTFE, while expanded uses fine powder. The differences on the raw materials can be seen on the table below. In this particular example, even though both resins have somewhat similar molecular weights, the average particle size of the skived resin is around 5% of that used on the expanded process. This has a huge impact on the fibrillation and therefore alignment magnitude of the resin. The higher the average particle size is, the higher the resin fibrillation capacity is. But how does that translate into performance? This slide brings a comparison of the PQR for the two materials we just described. The graph shows the PQR value for the skived gasket and the expanded using resin A. The skived is identified by the red color and the expanded by orange. The PQR was measured at 3 temperatures: ambient, 100 C, and 250 C. Comparing the red and orange bars, we can see how the manufacturing process has a huge influence on the creep of the material. The expanded gaskets were able to retain twice more load than the skived at elevated temperatures. Let's have a look at the 250 C test results, for instance, right here. The skived gasket was only able to retain 14% of the initial load. This is a very poor test result. Since 86% of the load applied on the gasket was gone due to creep, it is not hard to see that the chances of having leakage here are considerable. So after seeing this, what gasket, skived or expanded, are more adequate to your process conditions? I know it's not always easy to visualize what creep is and what effect it has on the gaskets, so we added this slide here to try to make it more ludic. This is not a PQR test done in the Untitled machine, but it's similar in many ways. The gaskets were installed in a rig and compressed using a bolt. The gasket stress was measured by the elongation of this bolt, and it can be seen on the dial. Dial moving clockwise indicates the load loss. The gaskets were installed with 26 megapascal and allowed to relax for 1 hour. The rig was then heated up to 302 F, which is 150 degrees C for another hour. So let's see what happens. "30 minutes into the test at room temperature, and it can already be noticed how much more stress loss the skived gasket has when compared to the expanded. We're going to start now the heating up phase. It's possible to see how immediately it affects the skived gasket. The stress just keeps on falling. Test now is about to end, and you can see how the skived have nearly half of the load retention expanded had. Very, very poor results once again. Here are the images of the gaskets before the test. And here are the images of the gaskets after the test. It is possible to easily see how much the idea of the skived gaskets has flowed and decreased. Let's add these two circles so that we can compare these changes with the original idea of the gaskets before the tests. Going back to the previous image, it becomes obvious how badly skived PTFE gaskets can be affected by creep. That's why special care must be taken if used at elevated temperatures. Let's have a look now at influences the raw materials can have under the same processing conditions. For this analysis, 3 different multi-axially expanded PTFE sheets were tested, each one from a different resin type with different molecular weights but using the same manufacturing process. We're comparing here expanded A that uses a lower molecular weight resin, which is the same material used on the previous skived comparisons, expanded B with medium to lower molecular weight resin, and expanded C with the highest molecular weight resin of the 3 samples. Raw materials can make all the difference. The resin type used had huge influence on the creep of the material, especially at high temperature. We can notice that the higher molecular weight resins have a tendency to give better creep results. If we look at the 250 degrees test results, for instance, it's possible to observe that the sample with resin A lost 34% more than the sample with resin C. And remember, resin A is the one we used in our Skype comparison. So if we had used resin B or C in our previous tests, the performance gap would have been much higher. With such a variance in the gasket's performance due to its raw material selection, how are the ePTFE gaskets available on the market looking like? Are they all similar in performance? Is there a considerable performance gap? We decided to investigate and obtain samples from 4 different manufacturers worldwide. We identified the samples as E1, E2, E3, and E4. The results did not surprise us. The performance gap among manufacturers is considerable. Even though all ePTFE gaskets tested had much better performance than the described material analyzed, it was observed more than 50% variation among the ePTFE products. Gaskets from manufacturer E2, this one, had much worse performance than gasket from manufacturer E4, this one. And remember, these are all gaskets that look very alike but are extremely different perform-wise. Not all PTFE gaskets are the same, and end users must be careful when making their specifications to avoid using products that perform like A2 when they actually need and expect E4 performance. Going to our conclusions, even though all materials tested have the same composition, which is 100% PTFE, the resin type and the manufacturing process had significant influence on the properties of the material, especially at elevated temperatures. The expanded material showed better PQR results than any SCIVE tested. And the ePTFE gaskets from different manufacturers had very distinct creep relaxation properties. I hope you enjoyed the presentation and thank you for your time. If you have any queries, please don't hesitate to contact us at brd@teadit.in.